Hi, I'm Sureintharaan, metrics number 217012. Today I'll be presenting on fluid features and dimension analysis. First and foremost, let's look into the definition of fluid. So what is fluid? Any material that continuously flows or deforms in response to an applied shear stress or an external force is considered to be a fluid. Since they have zero shear modulus, these substances are incapable of withstanding any shear force applied to them. Both liquid and gas may deform and flow to an outside force among these three states. As a result, both liquid and gas are considered to be fluids. Next, I would like to explain on fluid features. There are a lot of fluid features, but for this presentation, I will focus on the main 8 features, which are surface tension, pressure, specific weight, density, specific gravity, compressibility, and finally viscosity. Density: the density of a fluid is defined as the fluid's mass to the volume ratio. The density of gas changes with pressure and temperature, while the density of liquid does not change according to the pressure and temperature. Air has a density of 1.225 kg per meter cube, compared to water's density is 1000 kg per meter cube. And the formula given for the density calculation is rho equals to m over v, where rho is defined as density and m is equals to mass, while volume is v equals to volume. Next is specific gravity. The specific gravity of a fluid is defined as its density divided by the density of water at 4 degrees Celsius. The other definition of specific gravity is the weight of a given fluid divided by the weight of water at 4 degrees Celsius. Water has a density of 1000 kg per meter cube at 4 degrees Celsius. The formula given for to calculate specific gravity is specific gravity equals to density of fluid over density of water at 4 degrees Celsius, or specific weight of fluid over specific weight of water at 4 degrees Celsius. Okay, next will be specific weight. Specific weight of a fluid is the weight that it has per unit volume. The acceleration of gravity changes from place to place based on the specific weight. The specific gravity of water is 9.81 kilonewton per meter cube. So the formula given for to calculate specific weight is specific weight equals to weight over volume. Compressibility. Compressibility is a measure of the change in volume of a liquid due to a change in pressure. The usual quantity used to measure the phenomenon is the bulk modulus, which is E. Gases are generally more compressible than liquids. So the formula is E equals to negative delta P over delta V over V, where the delta P is the change in pressure and the delta V is the change in volume. So the next will be pressure. Pressure is defined as the amount of force exerted on a unit area of a substance. Pressure acts uniformly in all directions on a small volume of fluid. In a fluid confined by solid boundaries, pressure acts perpendicular to the boundary. So the formula is P equals to F over A, where F equals to force, A equals to the area of the unit area of the substance. Surface tension. Surface tension is the phenomenon that occurs when a liquid surface comes into contact with another phase. Water has a surface tension of 0.059 Newton per meter at 100 degrees Celsius and 0.079 Newton per meter at 0 degrees Celsius. So the formula is T equals to F over 2L, where T equals to surface tension and L equals to the length. The final feature will be viscosity. Viscosity is a measure of fluid's resistance to deformation at a certain rate. For liquids, it is equivalent to the common phrase, which is thickness. For instance, syrup has a higher viscosity than water. So the formula is F equals to mu times with A and times with U over Y. The mu is equals to viscosity of fluid, while the U over Y is equals to rate of shear deformation, and A equals to the area. In the next part of the presentation, I will be explaining about dimension analysis. Let's look at into the introduction about dimensional analysis. Dimensional analysis is defined as simplifying a physical problem by appealing to dimensional homogeneity to reduce the number of relevant variables. Basically, it is used to check equations, presenting and interpreting experimental data, attacking problems not amenable to a direct theoretical solution, establishing the relative importance of a particular physical phenomena, and also to physical modeling. Dimensions. A dimension is the type of a physical quantity and a unit defined as assigning a numerical value to that quantity. SI units are preferred in scientific work. There are two types of dimensions. One is fundamental dimension and one is derived dimensions. In fluid mechanics, the primary or fundamental dimensions are together with their SI units. For example, there are mass, length, time, and temperature, where mass the dimension will be capital M and the SI unit is kilogram kg, and for length the dimension is capital L and the SI unit is meter M, and same goes to the time and temperature. For time, the dimension is capital T and the SI unit is second S. And for temperature, the dimension is theta and the SI unit is Kelvin K. In other areas of physical, additional dimensions may be necessary. The complete set specified by the SI units consists of the below. For example, electric current, luminous intensity, and the amount of substance. For the electric current, the dimension is I, and for luminous intensity, the dimension is capital C, and for the amount of substance, the dimension is small n. While for the derived dimensions, in fluid mechanics, the secondary or derived quantities which possess more than one fundamental dimensions. For example, there are a lot of division in derived dimensions. For example, geometrical, kinematics, dynamics, and fluid properties. Since we are mainly explaining about fluid mechanics, let's look at into the fluid properties. The quantity, the quantity that are contained below fluid properties is density, viscosity, surface tension, and thermal conductivity. For example, the density's dimension will be rho, and the dimension is m, big, capital M, and L power of negative 3. And for viscosity, the common symbol is mu, and the dimension is capital M, L power of negative 1 and capital T power of negative 1. So these are the examples that consist under derived dimensions. There are a lot of theorems can be used for dimensional analysis, but for this presentation I chose Buckingham's pi theorem. So what does Buckingham's pi theorem explains about? If a problem involves n relevant variables and m independent dimensions, then it can be reduced to a relationship between n minus m and the non-dimensional parameters pi 1, it goes on till pi n minus m. To construct these non-dimensional pi groups, we have to choose m-dimensionally distinct scaling variables as known as repeating variables. For each of the n minus m remaining variables, construct a non-dimensional pi of the form pi equals to variable times with scale power of a, scale 2 power of b, scale 3 power of c, and it goes on, where a, b, c are chosen so as to make each pi non-dimensional. Here we have one example where the question asks us to obtain an expression in non-dimensional form for the pressure gradient in a horizontal pipe of circular cross-section. Then we have to show how this relates to the expression for frictional heat loss. So we'll start with step 1 where we have to identify the relevant variables. So for this question, there are 6 relevant variables involved, which is the pressure gradient dp over dx, density rho, v equals to velocity, and d capital equals to diameter, and ks equals to roughness height, and mu equals to viscosity. Then step 2, we have to write down all the dimensions that we identified in step 1. So for dp over dx, the pressure gradient, the dimensions will be m capital, L capital power of negative 2, and T capital power of negative 2. And for density rho, the dimension is m capital, L capital power of negative 3, and for velocity the dimension is L capital T capital power of negative 1,
And for diameter, the dimension is L capital, and for roughness side Ks, the dimension is L capital. And for mu, the viscosity, the dimensions will be M capital, L capital power of -1, and T capital power of -1. So after we write down all the dimensions involved in this question, we can proceed with step 3, where we have to find the number of independent dimensions and non-dimensional groups. So as we have already we found out in step 2 and step 1, we got to know that the relevant variables n equal to 6, and the number of independent dimensions that involved in this question, m equals to 3, which are m capital, L capital, and T capital. So for using the n value and m value, we can find the non-dimensional groups pi. So n minus 3 will get 3. So the non-dimensional group number will be 3. After that, we can continue with step 4, where we have to choose the dimensionally independent scaling variables using the m value. Since the m value is equal to 3, for this question we can take an example. We can choose d capital, we can choose diameter, velocity, and density as the dimensionally independent scaling variables. So after that, for step 5, we can create the pies by non-dimensionalizing the remaining variables. So the remaining variables are the pressure gradient, roughness height, and viscosity. So using the pi equation that I've already explained in the previous slide, we can create the general equation, which is pi1 equals to dp over dx times with d power of a, v power of b, and rho power of c. So considering the dimensions of both sides, we can substitute the equation with the dimensions of each variables. We can we can equate the powers of the primary dimensions to get the a, b, and c value. So after the calculation, we will get the a value, which is 1, and the b equals to -2, and c equals to -1. Later on, we can substitute all the a, b, c value in the pi equation. We will get the general equation, which is diameter times with pressure gradient dp over dx, divide with density, and times with velocity power of 2. The roughness height can be non-dimensionalized by inspection, since it already has the same dimension, which is L capital, as one of the scaling variables, which is the diameter. Since we have already know that the Ks equals to non-dimensional, we can find the pi2 is equals to Ks over diameter. Since Ks and diameter have the same dimension, which is equals to length L, so for pi3 we have to use the same general equation based on the previous slide. So we'll get pi3 equals to mu times with diameter power of a, velocity power of b, and rho power of c. So after we substitute all the dimensions into this general equation, we will get an equation with the a, b, and c value. So we have to equate the powers to get the a, b, c values, where we'll get a equals to -1, b equals to -1, and c is also equals to -1. Then we can substitute all the a, b, c values into the pi3. We will get pi3 equals to mu times with diameter power of -1, velocity power of -1, and rho power of -1. Where we can simplify it, we can get mu over rho times with v times with d. This equation is reciprocal to Reynolds number. So for step 6, we have to set the non-dimensional relationship between the pi1, pi2, and pi3. So we'll get pi1 equals to f bracket pi2 and pi3. So we can substitute the dimensions that we have calculated, that we have find out from the previous steps. So we'll get diameter times with pressure gradient over rho times velocity square equals to ks equals to function ks over d, comma mu over rho times with velocity times with d. So in step 7, we have to rearrange all the dimensions according to our convenience. So for this equation, we can, since pi 3 is reciprocal to Reynolds number. It's more easier to use, it's more accurate to use pi 3 power of negative 1 instead of pi 3. After that, we can also write the pressure gradient in terms of head loss, which is equals to dp over dx equals to rho times with g times with hf, which is the head loss over length. With these two changes in the non-dimensional relationship, we can simplify the equation, which will get heat loss equals to length over d times with v square over g times with the function ks over d and Reynolds number. Since the numerical factors here 1 over 2 can be absorbed into non-specified equation, this can be easily identified with the Darcy-Weisbach equation, which is hf, the head loss, equals to lambda times with length over diameter times with velocity power of 2 over 2 times with gravity, where lambda is a function of relative roughness, which is roughness height over diameter, and Reynolds number Re. That is all from me. Thank you.